My name is Chiamaka Ibeanusi, and this is my Physics Lab 3 report. The purpose of this lab is to create a unique star trajectory or orbit to find the mass of the black hole acting on the star in question and the initial velocity of the spaceship that will allow it to orbit around the black hole without crashing into it. Two computational models were used to achieve these goals, as you will see from the results, and the mass of the black hole was 1.186 times 10 raised to power 34 kilograms, and the initial velocity of the spaceship would be the vector seen. The main physics ideas used were the momentum principle, which was used to derive the velocity and position update formulas, and Newton's law of gravitation, as seen on the slides. This was used because of the gravitational attractive forces between the objects in the model. For part 1 of the lab, I aimed to calculate the mass of a black hole using the physics ideas mentioned before. The system is the black hole while the surroundings is a star. The mass of the star was given as 2.0 times 10 raised to power 30 kilograms, and the time interval was a day. The gravitational constant is 6.7 times 10 raised to power minus 11. The initial conditions are here in the code, as I mentioned before. For the loop, I was able to find the P to T, which is the change in momentum with time, and equate it to the F net, according to the momentum principle. After every iteration of the loop, a different mass would be calculated, so I put a counter to count how many iterations there were and average the sum of the masses by the counter to find the average mass of the black hole, which was given as from the beginning. I then found the parallel and perpendicular components of the P to T and equated them to the parallel and perpendicular components of the net force, respectively. Finally, I used Newton's law of gravitation to calculate the mass of the black hole using all the values calculated. The arrows on the star will show the components of the force in the parallel and perpendicular components. In part 2 of the lab, I used the mass of the black hole found in part 1 to calculate the initial velocity of a spaceship so that it would not crash into the black hole. The system is a spaceship and the surroundings are the planets and the black hole. The initial conditions are on the slide, including the calculated initial velocity. For the loop, I mainly used Newton's law of gravitation to find the net force on the planets and the ship respectively. I then used trial and error to find the initial velocities of the ship that would not crash into the black hole but come very close to it and move in the same direction as the planet. As you can see, the planet is in cyan and it orbits around the black hole while the ship is in magenta and moves close to it but continues moving away so it doesn't crash. Here is a close-up of the results for part 1 and part 2 respectively. Some possible sources of error in part 1 could be from the fact that the program could have been run for a longer time to get a more accurate mass of the black hole than was gotten. And as for part 2, due to the inaccurate initial velocities because of trial and error, or because of the time interval, which was very short. Comparing the two models wouldn't be accurate because the programs are used for different things, so I can't really find similarities or differences between the two models because they're interrelated. Now, you may wonder what the difference is between the parallel and perpendicular components of the net force and that of the rate of change of momentum. Mathematically, they are the same, but in this lab, the rate of change of momentum can be calculated directly with the given data, but the net force cannot be calculated directly without the mass of the black hole, which is what we are looking for. So in this lab, we are required to use the P to T to help find the net force. And let's say that instead of wanting to take a quick look at the black hole and leave, you decide you want to enter it and orbit around the black hole. To calculate the initial velocities to do this, it will take more trial and error to find the exact speed required to do so. If you start too fast, you will fly into the distance of space, but if you start too slow, you'll spiral into the black hole forever. So the precise velocity is very important. Thank you for watching, and I hope you learned something new.